For today's lesson, we are going to be talking about what's called partial fraction decomposition. So let's first talk about what this is. So partial fraction decomposition is the process of starting with what you might recognize as a simplified answer and taking it back apart or decomposing it so that it goes back to the initial polynomial fractions. And this method was introduced by a guy named John Bernoulli. From the do now, for example, you would add the two fractions together, get a common denominator, in order to move from the left-hand side to the right-hand side. So that would be what we call simplifying. Now what we're going to be doing today is we are going to be decomposing it. We are going to be writing it starting from the right-hand side and decomposing it into the initial two fractions that you added together. And so that is what we call decomposing. Now it might be strange that we are doing a process where we're kind of going backwards instead of trying to simplify something, but it is important to be able to decompose something complex like we have on the right-hand side so that we have simpler fractions to work with like the ones on the left, particularly when it comes to calculus. So I'm going to walk through all of the steps. Once you kind of get the hang of it and you practice, it's actually not too bad, but it is a number of steps to get there. So let's start with this. 3x plus 2 all over x squared plus x. So in this, we want to start by factoring the denominator. So the x squared plus x factors to x times x plus 1. And now what you're going to do is you are going to rewrite this, including one partial fraction with a constant numerator, and you're going to use a capital letter for each constant, for each power of each linear factor of the denominator. Now in this particular case, we don't have to worry too much about what this linear thing means for each one. In this case, both factors are linear. X only shows up once as a factor, x plus 1 also only shows up once as a factor. So we know when we are going to decompose it, we are going to have two fractions, one with a denominator of x and one with a denominator of x plus 1. And then for the numerator, you're going to use a constant, and we need to solve for what that constant is in the numerator. So we are going to, for now, use capital letters in the numerators. Now, if you rewrote it the other way, if you wrote a over x plus 1 plus b over x, that's fine. Your a and your b values will just be swapped, which is fine, because once you put it back into the expression, you'll have the correct number over the corresponding denominator. All right, so the next thing we're going to do, I'm just going to rewrite this at the start here. So what we're going to do now is we are going to multiply by the denominator to cancel all fractions. So our denominator was x times x plus 1, so we're going to multiply both sides by x times x plus 1. So multiplying this by x times x plus 1 completely cancels the denominator. We're left with 3x plus 2. If we multiply this times x plus 1, the x's cancel, so we're left with a times x plus 1. And then we multiply this times x plus 1, and the x plus 1's cancel, and you're left with b times x. So just a visual here of what's going on. So we're left with 3x plus 2 equals a parentheses x plus 1 plus b times x. So now you have your basic equation, no more fractions. You are going to distribute. So we have a times x plus b times x. And now what we're going to do is we are going to collect the like terms together and factor if it's factorable. So in this case, we have ax and bx, so I'll put those together. And then a is the only constant here. So now I'm going to factor that ax plus bx, so I'm going to factor the x out, and that leaves me with a plus b in parentheses times x. Now how do we actually go about solving this? We need to solve for a and we need to solve for b. Well, what we're going to do is we're going to look at either side of the equation and look at the corresponding parts. So if we look, the a on the right-hand side is the one constant, and on the left-hand side, the one constant is 2. So actually, we know that a has to equal 2. Now we can equate the coefficients of the x term. So we have the a plus b in front of the x here, and the 3 in front of the x here. So a plus b has to equal 3. Now in this particular case, using substitution is not difficult to solve this, but sometimes you might get a true system of equations where you have to solve for a, solve for b, using some sort of method of solving that system. For example, you might need to multiply one of those equations by 2 in order to cancel something out, but it's up to you if you want to do that or if you want to use substitution. Here in this case, it's pretty easy to use substitution because we've already found that a is equal to 2, so 2 plus b equals 3, which means b has to equal 1. Once you solve for a and b, you just want to go back to the very top where you started by writing a over x plus b over x plus 1, and instead of writing the a over x and the b over x plus 1, fill them in with the values that you just found. So a is equal to 2, and b is equal to 1, and so now we've successfully rewritten this 3x plus 2 over x times x plus 1 as the decomposition of two fractions. Let's look at example 2. We have x minus 23 over x squared minus x minus 6. Alright, so let's start by factoring the denominator. Factoring the denominator, that becomes x minus 3 and x plus 2. And now we can write this as an expression on the other side with two fractions, where one fraction has a denominator of x minus 3, the other fraction has a denominator of x plus 2. And in the numerators, we'll use a and b. Again, if your a and b's are swapped, so if you had a over x plus 2 and b over x minus 3, that's fine. Your a and b values will be swapped, but in the end, when you plug them back in, you'll have the correct corresponding value on top of the denominator. Alright, the next step is to multiply by x minus 3x plus 2 on both sides. So when we do that, let's see, this cancels. So we're left with just x minus 23 on the left, and on the right we have a times x plus 2 and b times x minus 3. So now we no longer have any fractions. We'll multiply this all out, so we have ax plus 2a plus bx minus 3b. Collect like terms together. So the ax plus bx I'm going to put together, and the 2a minus 3b, we know a and b are constants, and so that's going to be just a constant value, the 2a minus 3b, the whole thing there. And then let's factor where we can. So the a plus b times x is there. And then I'm just grouping the 2a minus 3b together. So this 2a minus 3b has to equal the negative 23. And then the a plus b here corresponds to the coefficient of 1 here. Okay, so writing those two things out, 2a minus 3b has to equal negative 23, and a plus b has to equal 1. Now it's up to you how you want to go about solving the system of equations. I'm going to use substitution. I'm going to solve for a in the second equation. So we have a is equal to 1 minus b. And now I'm going to substitute the 1 minus b into a in the first equation. So this is 2 times 1 minus b minus 3b equals negative 23. And now I have an equation that just has b that I can solve for. And once I solve for b, I can go back in and plug in and solve for a. So this is 2 minus 2b minus 3b, so 2 minus 5b equals negative 23. Subtract 2, we have negative 5b equals negative 25. Divided by negative 5, we have b equals 5. And now I plug b equals 5 into a equals 1 minus b, so I have a equals 1 minus 5, which is equal to negative 4. All right, so that means in this fraction here, we can go back and write in negative 4 for a and 5 for b, and that is our decomposition. All right, example 3. We have 5x squared plus 20x plus 6 all over x cubed plus 2x squared plus x. So we have to figure out how to factor out that denominator. So we can factor out an x to start, factor out that GCF. And then the x squared plus 2x plus 1, we can factor down to x plus 1, or in other words, x plus 1 squared. Now in the last two examples, we didn't have to worry about this because all of our factors only had a multiplicity of 1. When you have a factor in the denominator that has a multiplicity greater than 1, you are going to have to write an additional fraction with a new denominator where you add another degree. So let's just start with this. So we have 3 factors here. One is x plus 1, and one is x plus 1. Since x has a multiplicity of 1, we can work with that the same way we have with the last 2 examples. So we can write that that's equal to a over x. However, because there are 3 factors, we need to have 3 fractions. For the next fraction, the denominator will be x plus 1. But for the last one, it's not going to be x plus 1 as well. Anytime you have a factor in the denominator that's repeated, you're not going to write the same exact denominator as the one before, but you're going to increase the degree by 1. So here we have a over x plus b over x plus 1, and for the last one, c over x plus 1 squared. Now if in the denominator you had x plus 1 to the third, then you would add another fraction, and that would be d over x plus 1 cubed. So you want to have as many fractions as there are factors in the denominator, and if there are any repeated factors, you will want to start off with degree 1 for one denominator, and then go up by 1 degree until you reach the number of degrees that that factor goes up to. All right, so let's go ahead and multiply by x times x plus 1 squared on both sides. And on the left-hand side, that leaves us with 5x squared plus 20x plus 6. On the right-hand side, x's cancel here, so a times x plus 1 squared. The second one of the x plus 1's cancels. And in the third one, x plus 1 squared, that whole thing cancels. So we're left with a times x plus 1 squared, b times x plus 1, and then c times x. Now, if anything, this is actually more tedious than it is complicated. So we just need to multiply this x plus 1 squared, so that'll be x squared plus 2x plus 1, and then multiply that by a, and then distribute the bx, so bx squared plus bx. And then now you're going to do the same thing. You're going to group like terms. Now you'll notice that we did have 3 fractions, so we have a, b, and c to solve for. So we are going to have a group of x squared terms, a group of x terms, and then a group of constants. So grouping those together, we have ax squared and bx squared together. We have 2ax and bx and cx together, and then we have a. So factoring out an x squared, that leaves me with a plus b. Factoring out an x, that leaves me with 2a plus b plus c. And then the constant is just a. All right, so it looks like A is equal to 6. That will definitely help us here. And then we know that this 2A plus B plus C corresponds to the 20. And then the A plus B corresponds to the 5. So let's write that out as a system of equations. So A equals 6, 2A plus B plus C equals 20, and A plus B equals 5. There's your system of 3 equations with 3 variables. So since we know that A is equal to 6, let's go ahead and plug that into our third equation here and find B. So 6 plus B equals 5, which means B has to equal -1. Now that we have both A and B, we can substitute into the second equation. So we have 2 times 6 plus -1 plus C equals 20, and solve for C. So C is equal to 9. All right, so we have A, B, and C. Let's just put that back into our original form. So we have 6 over x plus -1 over x plus 1 plus 9 over x plus 1 squared. Let's do example 4. 3 over x squared minus 3x. All right, start by factoring. So this is x times x minus 3 in the denominator. All right, so we have 2 fractions. So that would be a over x and b over x minus 3. Now we multiply everything by x times x minus 3. That leaves us with 3 on the left, a times x minus 3 plus bx on the right. Let's distribute that a, so we have ax minus 3a plus bx on the right. Put like terms together and factor the x out, so we are left with x times a plus b. And now we can put corresponding parts together. So the -3a corresponds to the 3 here. Now you'll notice on the left-hand side, there's no x term. If you want, and if it helps, you can write 0x if it's helpful for you. So a plus b has to equal 0. All right, so here's our system of equations. So -3a equals 3, a plus b equals 0. Now we can pretty easily find the value of a in the first equation. So that gives us a equals -1. And since we have that, now we can plug that into the second equation. So we have -1 plus b equals 0, which means b has to equal 1. Plugging a and b back in here, we have -1 over x plus 1 over x minus 3. One last example. X plus 1 over x squared plus 4x plus 3. So start by factoring. So that would be x plus 1 and x plus 3. Write the 2 fractions, so that would be a over x plus 1 plus b over x plus 3. Multiply through by x plus 1 and x plus 3. Cancel things out. We're left with x plus 1 equals a times x plus 3 plus b times x plus 1. We'll distribute, so we have ax plus 3a plus bx plus b. Put like terms together, so the ax plus bx and then the 3a plus b. Factor out the x, and then let's match up the like things on either side. So 3a plus b corresponds to the 1. A plus b corresponds to, well, this is really an implied coefficient of 1. So those are my 2 equations. So 3a plus b equals 1 and a plus b equals 1. I have a system of 2 equations, 2 variables. So I'm going to take that second equation and I'm going to use substitution. So I'm going to solve for a, subtract b over, and now I'm going to substitute that into the first equation. So 3 times 1 minus b plus b equals 1. Distribute the 3. Combine like terms, so we have 3 minus 2b equals 1. And solve for b. So we have negative 2b equals negative 2. Divide by negative 2 and we get b equals 1. Now I can plug 1 in for b, and that gives us a equals 0. All right, so we have a equals 0, b equals 1. So now we can write this out as 0 over x plus 1 over x plus 3. Now you'll notice because a is equal to 0, that entire term is actually just equal to 0. Why does that happen? Well, if you look at the original equation, we had x plus 1 over x plus 1 times x plus 3. That can really be simplified by canceling out the x plus 1s, which would leave you with the 1 over x plus 3. So just notice that if you do have a 0 in the numerator, that means the entire term cancels out, and there's probably actually a simple way to simplify the problem.